Przemysław Narowski from Dr. Schneider company. And I'm glad that you are able to be here to watch my presentation, and we have the possibility to see each other somehow. But I also do really hope that in the next year, during the next conference, we will have the possibility to see each other in a direct way, shake hands, and enjoy all the coffee breaks. But so far, let us begin with today's topic. So for those who don't know me, I will just make a short introduction of myself. So I'm a mechanical engineer, and I'm in the industry since 2006, so almost 15 years. And I started as a machine setter at Coca-Cola, and afterwards I moved from all different positions in the industry because I changed companies. And since 2012, I only work for automotive institutions. I have experience with different special injection molding techniques like gas-assisted injection molding, injection transfer molding, and also Musel. I used to work with thermoplastics, thermosets, and rubber. But what's probably the most important for you as a guest of this conference is that I'm a certified Moldex3D professional. I've obtained the certificate after passing all of my exams on Taiwan in 2017. I got the certificate directly from Professor Chang, so the owner and the founder of the Cortec and Moldex3D software. In 2016, so a year before, I won a global simulation talent contest, and I received the reward during the K show in Düsseldorf in 2016. If you were able to attend previous conferences, so the real ones, the physical ones, which took places in Paris and Shanghai, you were able also to see me because I had presentations also during these events. So let's now talk a bit about the company itself, so about Dr. Schneider. So Dr. Schneider Unternehmensgruppe is a worldwide corporation which produces car interior systems. And here I would like to emphasize the name systems, because it is not only about such parts like this on the left, so a simple storage boxes, shelves, and so on, but it's about the whole systems which consist of plastics, electronic parts, and many more. And you can find it in all modern cars right now. So Dr. Schneider is not only a polymer processing company, an injection molding company. It makes and it deals with many other technologies, but of course, injection molding and polymers are one of the most important ones for a moment. I said that Dr. Schneider is a major producer of interior systems, but not only. It also makes parts that are exterior elements, like this one here on the left. It's a so-called fuel filler module, and actually that's the topic of our today's presentation. So here you can see all the areas of the car when you can find products of Dr. Schneider. One of these areas is, of course, this fuel filling space, when you can find this product, namely our fuel filler module, which consists of three major parts. One of them is housing, another one is lever, which connects the housing with the flap, and the flap, which is also made from plastic and needs to have the same color like the rest of the car body, which is quite challenging, and I will explain why. So if we analyze some particular dimension of our mold, it has a specific value directly after the machining. But during the production, during the injection molding, it becomes larger due to thermal heat expansion, which is also quite obvious. And our injection molded parts are also different. I mean, the dimension we are analyzing here becomes shorter due to shrinkage, warpage, and so on, which is also nothing surprising. And that's the value, that's the status we used to analyze during our injection molding simulation. The dimensions we can see and measure in our injection molding simulation tool. But in our case, the case of our flap, we need to paint it and dry it, and that this process needs quite high temperatures. Actually, it's something like 170 degrees of Celsius, so it's quite high for a plastic part. And because of that, due to these high temperatures, our dimensions, our specific dimension, which we are analyzing here, is getting even shorter, even smaller. But at that point, we are not able to predict it, to check it in our simulation software. In most of them, there aren't such possibilities, such modules like post-processing shrinkage processes or simulations. So how can we do it? How can we simulate our painting process and check the displacement and compare it with our design, and of course introduce some kind of corrections to our project in order to avoid any possible problems during the production, the assembly to the car, and so on. So we can use annealing simulation, which is a part of Moldex3D portfolio, I think, since a couple of years now. And that's how we do it, how we did the annealing simulation. So we use the real parameters, real process parameters from the injection molding machine, not the default ones or some kind of computed values. We use the 3D data of our mold to have the cooling circuits and the cold water geometry. And of course, we introduce the temperature profile from our painting and drying process, which in this case is quite simple. It's just 170 degrees. We are just keeping the part in 170 degrees for half an hour. And run a simulation and observe the results, which, as you can see, are not very satisfying at the moment. Yeah, on the left side, we can see the 3D scan geometry of our flap after painting and drying. And on the right hand side, you can see the results of our simulation. So the general picture is the same. The real part goes up and goes down in the same areas as it is in the simulation. But exact values are completely different. Especially here, we have the value that is more than 2 millimeters, and here is something like 0.2. So the difference between the simulation, our prediction, and the reality is almost an order of magnitude larger, which is not very satisfying. We can just make our model more complex. This is what we usually do for our simulations, for our cases. We just introduce additional boundary conditions, additional information into our input data. And so we did in this case. We tried to make the annealing analysis more accurate. And for that reason, we've changed the temperature profile. We introduced 2 additional days before and after the annealing, because the part isn't just directly taken from the injection molded machine after the injection and painted. It stays a couple of days in the warehouse, and it isn't also, of course, directly measured after the drying and the painting process. We also introduce fixed constraints from these hooks here. You can see on the picture on the right, because the part is dried in that position, so it hangs on these two hangers, and it's 3.5 millimeter thick, so it's also quite heavy. So we introduce also here a gravity force to make our annealing simulation more accurate. Yeah, and after running the results, running the simulation, we observe the new results, and we got a slight improvement, but only a slight one. Yeah, probably as you remember, here was something like 2 and something millimeter. Now it's 1.9. Here was 1.9. Now it's 1.7. So we are 0.2 millimeter better than we were before, which is still not satisfying for our purposes. So what can we do more? We can make another complication in our model, introduce more data. And the only thing which was missing at that moment, only thing we can introduce more, was the hot runner, the geometry of the hot runner. And so we did. We just took the hot runner geometry from our 3D data of the mold, and we ran additional simulation. And to our surprise, the improvement was a bit bigger than it was before. So this, we can see it actually here. Yeah, now it's 1.2, and it was 1.7. We started with 1.9. So the difference between the simulation before the difference between the initial simulation and the simulation with improved annealing model wasn't so great like it is now. So the introduction of the hot runner, of the geometry, made our simulation more accurate. And so at that moment, we can say that this makes no sense just to introduce more complexity in the modeling of the annealing process to make it more accurate, because it doesn't really improve much our results. The issue, the problem, is in the injection molding simulation, and in that case, especially in the prediction of the in-cavity pressure, because by introducing the hot runner geometry, we have introduced additional pressure loss in our system, and of course we change the pressure in our cavity during the whole cycle. So we decided at that point that the best way to improve our simulation, our displacement results, would be to improve the prediction of the in-cavity pressure, of the pressure curve during our cycle. And how can we do it? Probably, as you know, if we even have the same two machines, the same two injection molding machines made by the same producer in the same time and using the same place, in the same facility, even though these two machines have completely different ideas for generating these pressure curves for some reasons. So the only way to have this prediction really accurate, really corresponding to the reality, is to have this exact machine characterized. And so we did. We just characterized our machine, and we have put the new data of our machine into our machine data bank in Moldex3D, and we use it for a new simulation. And yeah, that was a good move, because right now we are in the same order of magnitude with our results and the reality and the results from the measurement, the geometry. And in some points we are really close, especially here. Yeah, the values are almost the same. So right now these results became useful for our purposes, for our product development process. Why is it so? Why we have such a improvement only by adding this additional step, only by having our machine characterized? Here's the answer. Here you can see the pressure history curves done for this particular point, so exactly inside our cavity during the whole injection molding cycle. And here you can see that the first two curves, the one which correspond to setting 1 and setting 2, are the same, because the only difference between setting 1 and setting 2 was the definition of the annealing process, the annealing simulation. So it didn't affect the pressure, and that's the reason why the curves are just exactly the same. Setting 3 was the simulation with this hot runner geometry, and here we can see a bit of a change. Yeah, the pressure is lower due to the pressure loss in the hot runner, but only the last curve, the orange one, which is our setting 4. So the simulation with the data of the machine, with the characterized machine data. And here we can see that the curve is completely different. The pressure is much smaller than it was at the beginning, and that resulted with a more accurate, better displacement results after the annealing. Here is a summary. You can see that for every setting, in every step, we're a bit closer to the reality, but only the last one done with data after the machine characterization is useful, actually. Yeah? Only the last one is brought us useful results, which can be utilized for further product development. You can also see that the discrepancy is getting larger in the areas which are more distant from the gate, which corresponds somehow to the pressure gradient, because the part is injected from the left to right, and we can see that the right hand side is the deviation of this simulated and measured values is larger at that point. So probably we are right with our assumption that the pressure and the pressure gradient in our cavity has really the largest influence of the final result of the displacement after the annealing. So in a conclusion, we can say that right now it is possible to predict, to simulate post-processing shrinkage-induced effects in Moldex3D. We can use an annealing simulation to predict displacement values after such processes like painting or annealing, of course, on any other which introduce additional energy, additional heat to our injection molded parts. But to have the results accurate enough for utilizing in our future product development, for our next steps, we need to have the simulation model complex enough. And the most important part of this complexity is the proper prediction of the in-cavity pressure. So we need to assure that the in-cavity pressure, the distribution, and the curve is pretty much the same as it is in the reality. And the only way right now to achieve it, to have it really done somehow, is to have the machine characterized. But can we do anything better? Yeah, of course. We can model also the machine nozzle and even the whole barrel to introduce additional pressure loss in our system and to see how the results are getting better. They should be. But the real thing would be just if we can compare the simulated pressure curves, simulated pressure values from our cavity with the reality. So the final checkup would be just to install pressure sensors in our mold and then compare the simulation with the real pressure curves and try to improve it. So that will be all for today. Thank you very much for your attention. Thank you that you managed to stay to the very end of this presentation. If you have any additional questions, feel free to ask me using this email address. And take care, goodbye, and see you in next year. Cheers!